Hello, everyone. Welcome back. Today we're going to be talking about Venn diagrams by John Venn. So basically, Venn diagrams, for anyone who hasn't seen them, they're basically these like circle diagrams that go like this, stuff like that. And then the things that apply to both you put in the middle, and then the things that just apply to one variable you put out here or out here for one variable the other, that sort of thing. So that's what I mean by Venn diagrams. So you've likely seen Venn diagrams before. You may have used them to compare and contrast in English. You may have used them for math before previously. So that's what we're talking about here, just to get the terminology out of the way. So let's talk a little bit about Venn diagrams. So first thing I want to introduce is the principle of inclusion and exclusion. Basically, if a collection of objects contains two types, with n1 of type 1 and n2 of type 2, and n12 of both types, then the total number of objects is n is equal to n1 plus n2, right? However, it's also important to note that there's times when that's not always the most accurate, because what if there's two different types of objects, but certain objects apply to maybe both or neither, or things like that? That's something we didn't really take into account here. This one's just saying, oh, it's as simple as just adding two numbers, which isn't really true, right? It isn't really as simple as just adding those two numbers in those situations, right? And so in those cases, if we have the sum of our objects, if we have our sum of objects, that's going to be equal to the number of things in A and B, A union B, which is equal to the number of things in A plus the number of things in B minus the things that are in both, right? Because we double count it here, right? So for example, let's say that category A is people who like pizza, and category B is people who like, I'm not sure, tacos, for example. Well, it's possible. Is it possible that somebody likes both pizza and tacos? Absolutely, yes, 100%, right? And so maybe there's 20 people who liked pizza and 20 who like tacos, but I only surveyed 30 people total, not 40. So how is that possible? Well, it's possible because perhaps some of the people said yes to liking pizza and tacos, but got double counted. So we have to subtract off the number of people who liked both pizza and tacos to make it work. Okay, so that's very important there. Okay, so I'm going to do an example to kind of illustrate what I mean, because I think this is one of those problems where it does make more sense when an example is actually given, and I haven't given one yet. So in this case, it says, last year, 12 players played basketball, 8 played volleyball, and 5 played both basketball and volleyball. If a dual team party was planned at Pizza Palace, how many seats should be reserved for the number of players in both teams? Okay, so what I'm going to do here is there's actually two different ways we can solve this, right? We can use the inclusion exclusion principle and a Venn diagram to figure it out. So I can say, well, the number of people total is what we want to figure out. The number of people in group 1, N1, is equal to 12. The number of people in group 2 is equal to 8. And the number of people in both groups is 5. So by this principle, we could argue that n is equal to n1 plus n2 minus n12, right? Because the people in both are being double counted. They're being counted at n1 and at n2. So we have to subtract them off once so that they're only counted once, right? So here we have 12 plus 8 minus 5, which is 15. At first glance here, we might think, oh, we have to save 20 seats at the pizza place because there's 12 members of the volleyball team 12 members of basketball and 8 of volleyball. But because 5 of those people are just the same people, we don't actually have to reserve 2 seats for people who play on both sports teams. There's still just one person. They still just need 1 seat. Very good. Now, what's another way to do it? We could say, well, here we have our Venn diagram. Let's have B be basketball and V be volleyball. So let's say B for basketball. And let's say V is for volleyball players. Okay, awesome. So what is going to go in the middle here? With Venn diagrams, we always want to start in the middle. Very important because it's much less confusing that way. So 5 players play both volleyball and basketball. So I'm going to put 5 in my middle. It also says 12 players played basketball. Well, the thing is, we already accounted for 5 of those players, which play both. So that means there's 7 who only play basketball, right? There's 12 who play basketball, period. And there's 7 who only play basketball and don't also play volleyball, right? And then the other 5 of them, the other 5 of those 12 players play both volleyball and basketball. And same thing with the next one. We can ask ourselves, well, we know 8 players play both, 8 players play volleyball overall, right? And 5 of them play both. So that means there's 3 of them left, 3 other players who only play volleyball and don't also play basketball. So we could also do it this way and say, okay, let's add the number of players who play just basketball plus the number of players who just play volleyball plus the number of players who play both, and we also can reach the same conclusion that way. So whichever way you prefer to figure it out is good, as long as you have a legitimate way of figuring it out, and you make sure to include the fact that there are some people who play both, and so we'll have to subtract them off again. That's the key thing here to remember, right? Because anyone can add 3 numbers together. What not everyone can do is necessarily know what's what, right? That's the most important part. Good. All right, let's do example 2 next. Example 2 says a scientist is looking for 2 traits in bugs, X and Y. Bugs are put into 3 categories, X, Y, and X intersect Y. The scientist cannot tell if the bug has a Y alone. If she examines 80 bugs and 34 have trait X and 12 have trait X intersect Y, how many have just trait Y? Okay, so in this case, let's think about that. Well, we know that N, the total number of bugs tested overall, is 80 bugs. We know that N1, right, the number of bugs that have trait X, is going to be 34. And we know that we don't know N2. That's what we're trying to figure out. We're trying to find how many just have trait Y alone, right? And we know that N1, 2, right? The ones that have both trait 1 and trait 2, right? So X and Y together is 12. So we can say that we know that N, the big N, is equal to N1 plus N2 minus N1, 2, and solve it this way. So 80 is equal to 34 plus N2 minus 12, which means that N2 is equal to 80 minus 22. So N2 is 58. Awesome. It's so good. Well done. All right, well, that is everything for that part. Now, let's say we want to figure this out in a different way, the Venn diagram way. Let's figure it out that way too. Well, let's have 22 here. Actually, let's draw a nicer circle in that. There's a whole circle drawing tool here for a reason. I'll make good use of it. There we go. That's much nicer, much better. Okay, so let's say this is trait X and trait Y, and each bug is either in one of these categories. So in other words, there aren't any bugs that don't have either trait. Every bug either has trait X or trait Y or both. Those are the only options. So we know that 12 have both, and we know that the number that have trait X is 34, and 12 of them are already accounted for in the middle. And so 22 are left, right? because this is going to be 34, which is our total number. So 34 minus 12, minus the 12 we already accounted for, will give us this 22. We also know that for here, we have 80 total for all the bugs, minus the ones that just have trait X, minus the ones that have both, is going to give us 58. So 58 must be the answer, therefore, because basically what we've done here is we've subtracted off everything else. We've subtracted off everything else in order to figure out that, oh, the only possibility is that there must be 58. Oh, and now I lost my circle. Let's put it back. Okay, good enough. Awesome. All right. Let's do one more example regarding Venn diagrams. This one is actually going to be a three-way Venn diagram, which is good as well. Oh. So this example says, if there are 100 grade 12 students currently at the school, use a Venn diagram to find how many only take chemistry if the number of students taking math is 52, the number of students taking physics is 38, the number of students taking math and chemistry is 35. The number of students taking math and physics is 15. The number of students taking physics and chemistry is 25. And the number of students taking all three subjects, math, physics, and chemistry, which is a heavy load, is 10. So I'm glad that's not too many people, because that seems like a lot of heavy stuff. Anyway, let's go ahead and draw a Venn diagram to illustrate this. And that Venn diagram is going to help us figure out how many students only take chemistry and don't take any of the other subjects. And keep in mind, one important thing to note is that there's 100 students in total. So if we add up all the other numbers of the people who just take math, people who take math and physics, people who just take blah, 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 and then, we're going to get some number, and then whoever isn't included in that must be the rest of the students who just take chemistry. The other assumption that we're making is that every student at this school, all 100 of these students must, and actually I'm going to add that to the question because I think that's a key point to keep in mind, is that all students must take at least one of these subjects, that there is no student out of these 100 students who doesn't take any subject, because if we don't make that assumption, then this is an impossible question to answer. We could say, oh, well, the answer, those people who aren't included at all so far with the Venn diagram, could those be students could they be not included because they're just taking chemistry, or are they, not included because they just don't take any of those subjects, right? So we're going to assume that every student at this school takes at least one of math, physics, or chemistry, even though I don't know if that's actually true. We're going to make that assumption. Okay. So let's do it. 1, 2, 3. Awesome. Okay, I'm going to actually, there we go. That's very good. Okay, so here we're going to do math, here physics, and here chemistry. Awesome. Okay, so what do we do with Venn diagrams? Rule number 1 is we always start from the middle, right? So 10 students take all 3 subjects, right? 10 students take all 3 subjects. So that's good. Okay. Now it says 25 students take physics and chemistry. Well, the thing is, 10 of those students here are already accounted for. So there's only 15 students who just take physics and chemistry but don't take math, right? Because remember, 10 take all 3, and those 10 are within this 25 as well. Keep that in mind. Now, what about math and physics? 15 take math and physics. 10 of those students are already accounted for in students who take all 3 subjects. So that means 5 must be here, right? Good. And then how many students take math and chemistry? Well, 35 of them. And we already accounted for 10, right? You take all 3. So that means 25 must take just math and chemistry and not take physics. Good. All right, now we know that 52 take math. So we've already accounted for 5 of those students here because they take math and physics, but not chemistry, and plus 10 of them here that take all 3 subjects, which includes math, and then these 25 who take just math and chemistry but don't take physics. So in total, 25 plus 5 plus 10 is 40. So that means that there's 12 students here, right? In order to reach 52, there's 12 students left in that 52 that haven't been accounted for that must take math, but not chemistry or physics, that take only math. Now it says 38 take physics, right? So we've already accounted for 5 that take math and physics, so that 5 there, plus 10 who take all 3, plus 15 who take physics and chemistry, so that total adds up to 30, right? So that means there's 8 students left who only take physics. 8 students who only take physics. Oh, and I lost my thing. Amazing. All right. Okay, so how do we find out how many students only take chemistry? Well, assuming that all students must take math, physics, or chemistry, and that it's not an option to be a student and not take at least one of those subjects, that would mean that the number of students taking chemistry would be 100, right? Because that's our total number of students, minus all these other numbers of all the people who are taking other stuff. So minus 12, minus 5, minus 8, minus 10, minus 25, minus 15, and that is equal to 25. So therefore, 25 students take only chemistry. Therefore, 25 students take only chemistry in this situation. Very good. All right, well, that is it for today with the Venn diagrams. Good work today, and I'll see everybody next time. Next time, we're going to be talking about combinations, which are similar to permutations but have a specific distinction that we'll discuss then. Good work, everyone, and I will see you all to discuss combinations next day. Bye, everyone.